these 3 talks. So the first day I will give some examples of Riemann surface laminations. I will give more examples, and Sunday I will give some further examples. Okay. So, you don't like? Okay. So, in order to begin by, I think, let me begin by the very well-known basic theorem in dynamical systems, real dynamical systems, which is the Poincaré-Benediction theorem. So almost all of us know that if you have a vector field on a 2-sphere, and if you want to understand the dynamics of this vector field, this theorem is really the very first and most important of all of them. It says that if you pick any point on the 2-sphere, and if you draw the trajectory going through that point, then you have 2 possibilities. Either, not either actually, or the trajectory contains, no, I mean, it could be both. It could be both. Either the, how should I say in English, if it could be both? Yeah. What? Or? This is not exclusive. Okay. Okay, so I say that the closure of any orbit contains a singular point or a periodic orbit. This okay, so this, I think we all agree that theorem, and we all try to have a similar statement in the complex domain. And this is one of the motivations for me of looking at this kind of problem, is a conjecture that I think is due to Camacho, which is the following. You consider in the complex 2-plane C2, you consider a differential equations dx dt is equal to pxy and dy dt is equal to qxy, where x and y are complex numbers and p and q are 2 polynomials in the variables x and y. Now, you, instead of looking at the orbits as before, you look at the leaves, because now it's a 2-dimensional, it's a complex 1-dimensional dynamical system, so you can think of the orbits as being, as Ilyashenko was drawing yesterday, Riemann surfaces in C2, and in order to make things compact, you compactify the foliation in complex projective space, and you have a very nice object in CP2, complex projective plane of dimension 2, with some singular points corresponding to the common zeros of P and Q, and some regular point, many regular points with Riemann surfaces going through them. And the conjecture of Camacho is that something like Poincaré-Benediction theorem should be true. The closure of any leaf should contain at least a singular point. It is not difficult to see that the other case, the case of periodic orbit or compact leaf, does not occur. So the conjecture is that there should be some very general statement about differential equations in C2. The closure of a leaf should contain a singular point. And this is a nice conjecture which I will not say anything about it, or almost, I would say almost nothing about it today, but it's something like a motivation around all of these questions. When I wrote this yesterday, I wrote this yesterday night when I wrote this transparency, I wrote conjecture, but today I'm not, I'm changing my mind every day. Maybe it's not true. By this conjecture of Rebe, which was conjecture for the real codimension 1 foliations, which was that there should not exist exceptional minimal sets for codimension 1 foliations. And people were working hard to prove that. until Riemann had the good idea of opening the collected papers of Poincaré. And he realized that these 11 volumes were just full of counterexamples. And so I was thinking, maybe we should open some other book. And I have a suggestion. My suggestion is this. We should read the collected papers of Painlevé. I think Painlevé has been forgotten. Paul Painlevé.
Right.
Yeah, he has been forgotten. He has done a wonderful work. It's difficult to read. It's written in French. But really, I believe it's a good idea to open these collected papers. Only 2 volumes, I think. You know.
From a historical point of view, his work is the starting point of the theory of foliation.
I think so, yes, for sure, yeah, for sure.
And it's really this
Yeah. Yeah. Okay, so suppose this conjecture would be not true, then you would have a leaf which would not accumulate. Then the idea of that leaf, and it would be a lamination. So this is why what we want really to look at is how bad, how is it possible to look at Riemann surface laminations inside complex projective space? And this is what I want to look at in this series of talks. So, okay. So before I go on, because there are so many notions of Riemann surface laminations and so on, or laminations at least, I think it's a good idea to fix the notation and definition. We had several definitions of laminations in this meeting. Give it quickly what I mean by here. I mean just a compact metric space X, which is filled by Riemann surfaces, the green leaves, with the property that you can cover the compact space by flow boxes, the red boxes, with charts phi I, which go onto a product D cross Ti. D is the unit disk in C, and Ti is some transversal locally compact metric space. And I want the change of coordinates Hij to have the form which is indicated here. Hij is of the form Fij of Zt, comma, Gij of T. And the important fact is that I want Fij of Zt to depend holomorphically in Z and continuously in T. So this is maybe the main difference between what we had already in this conference. I want to insist on a conformal structure along the leaves. So the leaves are Riemann surfaces. The change of coordinates depend holomorphically on Z. I'm not going to work from the holomorphic structure. So this is what a Riemann surface lamination is, and that I would like to develop in this series of lectures is we would like to understand these objects by themselves. And hoping we understand them enough, then we can ask, can we put such an object in CP2? So I want to split the question in 2 parts. I want to understand these objects as by themselves, and then ask the question, what about? So this is general idea. One further definition to make things simpler is the following. Just like for Riemann surfaces, irreducible or connected Riemann surfaces, I want to introduce a very simple concept. We say that the Riemann surface is minimal is dense in it. And by using a very elementary Zorn's lemma, it is easy to see that every Riemann surface lamination contains at least one minimal sublamination. So sometimes I will restrict myself to minimal laminations. Because if you embed in CP2 a lamination, in particular you embed every sublamination, so you can assume that the object you're looking at is. So this is the general purpose of the talks will be try to understand and develop a theory of Riemann surface laminations as similar as possible to the classical theory of Riemann surfaces. That's the general purpose. Now, what is classical Riemann surface theory? It's a big subject, but there is one theorem, which is a wonderful theorem, maybe one of the most wonderful theorems in mathematics, I think, which is due to Riemann. Riemann proved this wonderful fact that any Riemann surface is algebraic. In other words, if you give me an abstractly defined compact Riemann surface, it is always possible to embed it into some complex projective space. And this is the typical question that we would like to try to understand. Is it possible to prove similar statements about Riemann surface laminations? Is it possible an abstractly defined Riemann surface lamination? Is it possible to put it holomorphically, of course, inside some projective space of some? And this will be one of the central questions I will try to look at today and tomorrow. Now let me try to restate the conjecture of Camacho in a more general setting, which is closer to what I just said. The conjecture now has nothing to do with polynomial differential equations in C2. There is no more P and Q and dx, dt and things like that. The conjecture now is this. Start minimal Riemann surface lamination. And suppose this lamination embeds in P2, holomorphically. And the question is, show or prove or disprove that this lamination has to be trivial in the sense that it reduces to just a simple leaf, a simple compact Riemann surface, the trivial case. So that's another way of thinking of this. This conjecture is, of course, stronger than the conjecture of Camacho because we do not assume here, we do not assume that there is any kind of global holomorphic foliation for which this lamination would be tangent to it. Abstract embedded into P2. That's another way of thinking of this conjecture. So I told you examples. Let me begin by the very first family of examples. I mean, the examples that we just already saw many times in this conference are foliations on three manifolds, for example, the examples that David Gabay described. So in order to put this right in the context, I recall the very classical fact, which is earlier than Gauss, than Riemann, it's due to Gauss. It tells you that if you take any Riemannian metric or piece of Riemannian metric, it is always possible to locally find conformal maps into the complex line C. And any two of these conformal maps are related by a conformal map of C that is a holomorphic map. So this means that if you give me any Riemannian metric on a surface, then this Riemannian metric defines canonically a complex structure on it, and so that you can think of the Riemannian metric on a surface as being a Riemann surface. Now if you have a manifold, compact manifold M, and if on this manifold by two-dimensional leaves, And if, moreover, you give me a Riemannian metric along the leaves, that each leaf is now equipped canonically with a of the Riemann surface. So really, you get a Riemann surface lamination. So one way of thinking, one way of producing many examples of Riemann surface laminations is just this one. You put a manifold with a two-dimensional foliation. You choose a Riemannian metric on it. Then you're done. This gives you a Riemann surface lamination. So this provides you with many, many examples of Riemann surface laminations. So let me give you one theorem I'm going to prove in the third lecture, going in the direction of what I meant before, trying to know if an abstractly defined Riemann surface lamination can be embedded. Here's a theorem. We shall see that Sunday. Theorem is this. Start with a two-dimensional taut foliation on a manifold. Put on the tangent bundle any Riemannian metric and think of this object as Riemann surface lamination. Theorem is, then, this object can be put in some projective space holomorphically of some dimension. Of course, the dimension n here by transversality condition n is equal to 4 should be enough. So you can put your favorite, David Gavai gave us many examples of three manifolds with nice taut foliations. All of them can be put in Pn. Unfortunately, not in P2. That would be counterexample to Camashaw's conjecture. But in Pn, you can do it. By dimension theory, an embedding in some high-dimensional projective space, you can project it back on some lower dimensional projective space. So the only problem is to make sure that the composition of the embedding and the projection is still an embedding. So it's a counting dimension. It should be 2n plus 1. So 2 times 3 plus 1 is 7. So 7 is less than 8. So this said complex projective should be enough. But
you count the complex dimension, S has dimension 1, and then you need 3.
No, because there is transversal direction. No, you cannot forget it.
Pretend it's degree 0. Pretend it's Cantor set.
Yeah, it's not Cantor set. Yeah. If it were Cantor set, I would.
Split it.
No, I want embedding, continuous embedding. Yeah. If you split it.
It's often the topology to get it into CP3.
Yeah, you're right. I agree with you.
Does that work?
Yeah, that works. Yeah. No. So this is the typical example of something I want to do. Of course, I'm not very happy with the theorem. I would like to get some more general. I will explain that later. But this is a sample of what we would like to get.
Can you say one sentence about the idea of the proof?
You want the idea of the proof?
Just one sentence.
If I give you the idea of the proof, you won't come back on Sunday.
Just the answer, is it Partain Taylor?
No. Okay, so, show that many laminations embed. And, it's always a problem to give a talk which is supposed to be elementary in front of so many experts. So I decided to do some exercises. The experts can try to do the exercises while they are not listening, and those who want to me, listen to me. Okay. So here's the first exercise. Here's another very nice and classical example of lamination. You start with a discrete subgroup of SL2C. We like these examples, Kleinian groups. You assume that the quotient 2C modulo gamma is compact manifold. There are many examples, as we know, of such a situation. Translation on this coset space SL2C modulo gamma by upper triangular matrices 1, 0, T1. This gives you an action, holomorphic action of C on this compact manifold. In the same way, you can look at left translation by a diagonal matrices, omega 0, 0, omega inverse, where omega is a non-zero complex number, C-star action, holomorphic C-star action on this complex manifold. So now, in this way, you get a nice foliation F1 by holomorphic curve on this 6-dimensional real manifold. Let's forget of the complex structure. In the same way, we have another nice 2-dimensional foliation on a compact 6-dimensional manifold given by the orbit of the second action. So really, on this real compact 6-dimensional manifold, we have two nice examples of Riemann surface laminations. Orbits of C and orbit of C star. So the complex structure is obvious. And the exercise for the experts, and also for the others, to show that it's not always true that you can embed in complex projective space. The exercises show that none of these two examples can be put inside, holomorphically embedded into some complex projective space. So, you know, sometimes it works, like the theorem on taut foliations. Sometimes it doesn't work. Some don't embed. Some you know, when I was speaking of experts, I think I was thinking that you are one of them. What? No, for example, if you want bedding, topology. Okay, let me give you another example, or another examples. Also, that will be an exercise for experts. The other family of example is this. Here's a very simple way of constructing examples of laminations. It's the following thing. General construction, which is very simple. You start with a of SL2R on some compact metric space. Then you say, well, in SL2R, there's a subgroup which is SO2. SO2 is a compact group. So it's a good idea to look at the quotient. Let me call it K bar, which is the quotient of K of SO2. So usually it's a very nice object. You have an action of a circle on a compact space. The quotient is usually a very nice compact space. And now, since you had an action of SL2R on the compact space, typically with three-dimensional orbits, because SL2R is dimension 3, when you go to the quotient by SO2, is foliated by copies of SL2R modulo SO2, which is a Poincare disk. So typically, in general, in many cases, we get a lamination on this space K bar by the orbits of SL2R modulo SO2. In general, it's not always the case, it's not always lamination, because some orbits have lower dimensional orbits, have a lower. Is really like a lamination which is singular. Some orbits are two-dimensional, some are one-dimensional, and maybe there might be even some fixed points. But in some cases, you get some nice object. So let's give one example, and that will be the exercise also for the experts. The example is to look at the space S of Schlicht function, or univalent functions. That is, you consider the space of all holomorphic injective functions from the unit disk D into the complex number C with this normalizing condition that f of 0 is equal to 0 and f prime of 0 is equal to 1. So it is well known that this space endowed with the topology of convergence, uniform convergence on compact sets, is a compact space. And on this compact space, there is a natural action of PSL2R. What is it? Well, if you have a map, equivalent map D to C, if you give me an element of PSL2R, you can let it act on the source. So you get another map from D to C, just by precomposing with PSL2R. You get a new map which is still univalent from D to C, but maybe it's not sending 0, probably it's not sending 0 to 0 and has not the right condition for the derivative. But then you post-compose it by some affine map to come back to come back home, to make it sending 0 to 0 with one derivative. So this gives a very nice and natural action of PSL2R on the space S, which is a nice complementarizer. Well, quotient S modulo S, because after all, it is identified canonically with the space of all simply connected domains in C, modulo containing the origin, modulo the equivalence relation of a similarity. Because if you give me a simply connected domain in the plane, you can uniformize it by Riemann theorem. This gives you a univalent map, maybe not with the right derivative, so you can rescale it. But this gives you an element of S, which is well defined up to rotation. And conversely, if you give me an element of S, look at the image of the disk, it's a simply connected domain. So really this S modulo S2 is a nice, interesting space. This is the space of open domains, simply connected domains in the plane, which is compact metric space. So in other words, on this very natural and very important compact space, we have some kind of lamination. So the exercise is the following. First, try to understand, to describe which orbits, which leaves have dimension 0 or 1. Okay. In other words, as I told you before, this process of constructing a lamination from an action of SL2R is not always okay. I mean, sometimes some orbits are not of the right dimension. So the exercise is first try to understand which is the singular locus, which domains have a one-dimensional or zero-dimensional orbit. And the second question is it true that, or not true, that any orbit, two-dimensional orbit, accumulates to the singular locus? If not, the closure of a two-dimensional orbit like that will be a very nice lamination. A very nice lamination, a real lamination with the actual definition. So you get many examples like that. So that's a good exercise. So either you do it now, or this is homework. Since it's a mini course, I'm allowed to give homeworks. Yeah? So this is homework. But you know, this is a very complicated object. Understanding the dynamics of this lamination is, I think it's beyond many things. I mean, it's a very, very complicated thing. This second family of examples. Yeah. Right. One more example. Is a bit similar to the previous one in the sense that this is kind of a universal object too. It comes from tessellations. You know, these kind of Penrose tilings and things like that. So here's an example. You consider the three polygons I drew on the top of the transparency with strange, funny shapes. And it turns out that it is possible to tessellate the plane with pieces which are like that. Well, to be completely correct, I should allow myself not only these 3 pieces, but also their reflections, vertical or horizontal. So actually I should more tiles. And of course I could do that with easier shapes, but the point of this is that these shapes have been chosen in such a way that it is possible to tessellate with these shapes, but it is not possible to tessellate periodically. So these polytopes, these polygons, have been chosen in such a way that they tessellate non-periodically the plane. And the point is that not only they tessellate the plane, but they tessellate it in many ways. So one way to understand this situation would look at the set of all possible tessellations of the plane R2. I put here R pointed at 0, fixing the origin, by polygons on P2, P3, or the images under reflections. So this is a very complicated set, and on this set you put natural topology. You say that 2 tessellations are nearby if they agree on a big ball. So you take 2 tessellations by these polygons, and you have a very big ball. If you see the same picture on that big ball, you say that the 2 tessellations are close. This defines a topology, and if you think a little bit, you will see that this is a compact topology, compact metrizable topology. So really, the space of all possibilities of tessellations is a compact metric space. Not very bad, not very nice space. And on that space, there is a very natural lamination. Just move the base point. If you have a tessellation of the plane, you can just translate it. If you translate it, you get another tessellation because you have, this is an isomorphic tessellation. It's a different tessellation because the origin is not the same. So moving the origin along you get a full leaf going through this compact space, and the fact that these polygons do not tessellate periodically the plane means that this lamination has no compact leaf. Moreover, and this is an exercise for you, the sentence I just pronounced, that there is no compact leaf, implies that all leaves are simply connected. So all leaves are copies of R2, really R2. So we have a very nice example, mentioned by Euclidean leaves. Each leaf is a copy of the Euclidean plane, and each leaf is dense in it. That's another fact. This is a very also complicated object, which is transversally like a Cantor set. And we shall see Sunday that this embeds a complex projective space of dimension 3, because it's transversally 0-dimensional.
Are you claiming this is a Riemann surface lamination?
Yeah, this is, it's even better. The leaves are a C. It's even the change of coordinates are not holomorphic functions; they are translations. And well, who is more holomorphic than translation? Yeah, so that's a nice example. Now, next example. If I were serious, I wouldn't give it because the time is flowing faster than I was thinking. But I would feel guilty if I would not speak about it, because it's the name of this is the email address of this meeting. We have to speak of solenoid sometime. I think it's we had some solenoids yesterday, but I think it's such an important construction. Most of you know it, but I want to describe this. So this is, I think, due to Sullivan, this construction of solenoid, is it? Okay, I think so. So let me explain this construction. Before I give the construction, I want to make a simple remark, which is this. Suppose you have a germ of a holomorphic contraction of C at the origin, F. Then what you do is that you take a small domain U in which the germ is defined, take its image, and you take the quotient of this domain U minus the origin by the dynamical system F. In this way, you construct a Riemann surface which is holomorphically an elliptic curve. It's a torus with a complex structure. So there is a way of going from germs of holomorphic maps which are contracting to elliptic curves. And the simple observation is that these two things are just the same. If you give me a germ, I give you an elliptic curve with a homotopy class, and conversely, if you give me an elliptic curve with homotopy class, then I give you a germ to conjugacy. So this is that shows you that you can associate to a dynamical object like F a geometrical this elliptic curve is dynamically defined. And the idea is to try to do things like systems, like an expanding map of the circle S1. So what I want to explain to you is how it's possible to associate of say class say infinity, which the derivative is bigger than 1 everywhere, associate surface lamination, which is canonically associated to it, and in such a way that the Riemann surface lamination contains the dynamics of F. The geometry of the Riemann surface contains the dynamics. So the construction has several steps. Explain it. The first step is to replace the expanding map F by its natural expansion. That is, you have a map which is non-invertible from the circle to itself, which is expanding, and you construct another space that I denoted by S1 hat, which is the space of sequences xn such that f of xn is xn plus 1. In other words, S1 hat is the space of two-sided orbits of f. This is a compact space which lies over the circle S1 because you have a natural projection pi which maps the sequence xn to the point x0. And the nice feature of that is that the non-invertible map f at the level of the circle lifts on S1 hat as an invertible map f hat, which is homeomorphism. So this is a nice feature. We replace something which is non-invertible by something which is. The bad feature is that we had a very nice circle, and now we have a more complicated object, which is a solenoid. And this complicated kind of fibers over the circle choices of the past for one orbit. So that's the first step. As you see, this one-dimensional solenoid S1 hat is kind of laminated, but now the leaves are one-dimensional. They are lines, real lines. So that's the first step. The second step is we want to analyze these one-dimensional lines sitting inside S1 hat, and we put on it an affine structure. So the point is this. I claim that these green lines sitting inside S1 hat, each one of them has a natural affine structure, meaning, in particular, to express it in the most natural way, meaning that if you give me 2 points on the same green line, I can define canonically the middle point. And the way of doing it is this. You take your 2 points x and y on the same green line. You take the image of these 2 points by the inverse, by f hat to the minus n. This makes sense because this is a homeomorphism. You get 2 points that are denoted by xn and yn, which are now very, very close together because the map was expanded, is contracting. Now you take a middle point of x and yn, you call it zn, but nothing. So you choose an auxiliary Riemannian metric. Anyone. And for this Riemannian metric, choose the middle point, take the middle point, n, of this very tiny interval going from xn to yn. So you have very, which is right in the middle of these two, x and yn, you put back by f hat to point, which is somewhere in between x and y. However, this choice, this point depends strongly on the do this with very, very big n, do this and look at the limit of these points in this interval xy and show this is converging and show that the limit does not depend on anything. So really it is possible to canonically on this space S1 on each green line, it's possible to define an affine structure. So that was the second step. The third is to remark that the affine line is the boundary of upper half space of the upper half. So the third step is to observe that the affine line, you can think of it as being the boundary of upper half space in Poincaré model. So what you do is take your space S1 hat and above it, for each one of these green lines, well now you know this green line is an affine line, you put vertically a copy of the Poincaré upper half space. This makes sense because the way this how can I say that? This makes sense because affine transformations on the line induce isometries of upper half space. So you get a complicated object which sits, which is non-compact, which is vertically above S1 hat. Somehow the boundary of this object S1 hat. And a nice fact is because the construction action of F hat acting on S1 hat lifts to an action of F1 on this space hat on this space is upper and free can go to the quotient and a compact space which is foliated by these vertical leaves which are copies of the Poincaré half space. So finally what you get associated with the original F, you get a Riemann solution on a compact metric space which is kind of canonically associated to the expanding map F. And one of the nice features of this construction is that we have the following theorem so you will tell me, I think it's typical leaf is a copy of A of H2, a typical leaf. What? It is dense. All leaves are dense. Most of them are copies of H2. And corresponding to each periodic point, you have a hyperbolic cylinder. And this observation is the key of the theorem that I think is due to Mike Shub and Sullivan, but I'm not sure. Is it? Is it your expanding map? And,
We prove it.
yeah, you prove it. I mean, Mike is should be here. Yeah, yeah. Which says that this construction is rich enough to remember the dynamical system F. In other words, if you give me two expanding maps, F1 and F2, and if you look at the corresponding geometrical objects, which are the Riemann surface laminations, then the following are equivalent. F1 and F2 are conjugate by, say, infinity diffeomorphism. The corresponding solenoids as geometric objects are biholomorphic. So really, very naive case of a contraction, you can in a geometric solenoid of F. Okay.
This paper appeared some years before the
Construction, yeah, I know, but that follows almost immediately. Yeah.
paper was with the eigenvalues and the expanding map.
Yeah.
Then you observe the eigenvalues
Moduli.
and the moduli at the
Yeah.
end of
Okay, I think, let me go on. One of the things that we would like to do with Riemann surface laminations, if really we want to consider them as being kind of generalizations of Riemann surfaces, would be to be able to find a fundamental class for them. You know, this is very important for a manifold. A manifold has a fundamental class. So we would like to do some kind of homology on a Riemann surface lamination, and we would like to do as much as possible to try to make the theory of integration of differential forms and things like that on some kind of fundamental class. So before I explain what's happening, I'm defining some very trivial things, just like for any manifold on which you can define differential forms. If you have a Riemann surface, you can define differential forms. Of course, by differential form, I mean something which is defined only along the leaves and which is continuous in the transversal direction. So I define differential forms along the leaves. So I have omega 0 is nothing more than functions on the space with differential forms of degree 1. Omega 2 is the differential forms of degree 2. So these are objects which are defined along the leaves and moving continuously in the transversal direction. I have a very complex differential going from functions to forms and from one form to two forms. So this usually it's useless. Usually. So one way of trying to mimic the definition of integrations of forms and manifolds and things like that has been introduced by Sullivan. Let me give a definition. A foliation cycle, or one could say a fundamental class, for a Riemann surface lamination is something that allows you to compute the integral of a two-form. After all, our Riemann surface lamination, we want to think of it as being some kind of two-dimensional manifold. When you have a two-dimensional manifold, well, you want to be able to integrate forms of degree 2. So that's what we want. We want some operator I from to real numbers. I of some form will be called the integral of the form. And the conditions that we want to impose on I are written there. First of all, I want the integral of the positive form should be positive. What's a positive form? Well, on each surface, and therefore it's oriented. So it makes sense to speak of a positive two-form surface lamination. So of course, the minimum that we can require is that the integral of a positive form should be positive. And the most important condition, the second condition, is that we want to impose Stokes' theorem. We want that the definition, if you have a lamination, we would like to have such a foliation cycle. If you have such a foliation cycle, somehow your lamination looks very much like a compact Riemann surface. Of course, the question is to know if this kind of object exists. And there is a description of them, which is also due to Sullivan, which is the following. We had several times discussion about transverse invariant measures. And let me say that quickly. If we have a invariant measure for lamination, as you know now, the way that the thing is. So if you have such an invariant measure, you can define a foliation cycle. How do you do? Take a form omega, 2 omega, and assume first that this has a support which is contained in the foliation chart, d cross ti. So what you can do is that you can integrate in the usual sense the form omega on d cross a point. You get a number, and this number you can integrate it against the measure mu I. And you get a number omega this way. Transversal. Form omega does not have support contained in then you multiply it by a partition of unity, and you do this piece by piece, and you check that the result is well defined. In this way, you show that any transverse invariant measure defines the foliation cycle. And the main result is that this is the only way. This is bijection. The foliation cycle, transverse invariant measure are just the same objects. Any foliation cycle is obtained by this construction. All my laminations are, but I'm not sure. In this case, is it important? I don't know, but in my case, all things are compact here. Closed currents, yes, exactly. Yeah. Okay, so now the problem is to find.
Kind of a local result. So
Yeah.
Think of a locally compact version.
Yeah. Then you have to change the. Yeah, you have to change definition. I mean, forms, compact support, and things like that. Okay. Now you can ask yourself, do these objects exist? And you have a nice theorem, also due to Sullivan, which says the following. The existence of a transverse invariant measure, or if you prefer, the existence of a foliation cycle, is equivalent to the non-existence of a positive exact two-form. It is clear that if you have a positive exact two-form, that these two things are equivalent. And of course the proof, of course the proof is just, just obvious. Is this, you look in the topological vector space of all two forms, you have a cone, the cone of positive forms, and you have a subspace, the subspace of exact two forms. And you can have two possible configurations. One, the subspace could intersect the cone only at the origin, or the subspace could intersect the cone non-trivially. In the first case, in the second case, well, we have, by definition, we have a positive exact two form. In the first case, since the cone and the subspace are disjoint, by Hahn-Banach, there is a linear functional on the space which is positive on the cone and 0 on the subspace, which means precisely that there is a foliation cycle which is a foliation cycle. So there is no proof, just look. Okay, so this is a neat theorem, but you know, it's good and not good because, well, we must say that usually there is no transverse invariant measure, and it's not clear if Riemann surface laminations with transverse invariant measure are the most interesting things to look at. The basic question. However, I want to finish the talk by one theorem which I put many names. Who proved what? Doadier told about, I don't know, this old theorem. But it tells you the following thing. It's related to the Kamash's conjecture I mentioned at the beginning. It tells you that, you remember, I hope, that the conjecture was that in P2 there is no non-trivial Riemann surface lamination. That's the question. That there is no non-trivial Riemann surface lamination admitted. If you put the additional condition that the Riemann surface lamination admits a transverse invariant measure or foliation cycle, if you prefer, this kind of object does not exist. So that's kind of a first step toward, you know, the assumption of the existence of a transverse, very, very strong one. So let me sketch the proof of that, and that will be it. The proof will be this. But did I?
You can drop it, but the proof shows it.
No, you need holomorphic. I think so. Yes. Yeah. I think so. I mean, otherwise I could find plenty of counterexamples. Okay, so the sketch of the proof is this. Suppose by contradiction that in CP2, in complex projective space, you have such an object X, which is the Riemann surface lamination with a foliation cycle. Then, well, you observe first that the complex of two forms on CP2 can be restricted to two forms on the object X. So this gives you a linear map from two. I assume a linear map, an integration map I that allows you to integrate. Put this on two forms on CP2, and this linear map vanishes on exact forms. So what you really get is a homology class in CP2. Call it C. This is a homology class in CP2, or a cycle, if you prefer. Then the proof will be by contradiction. We will show first that the self-intersection C intersection C is positive, and then we will show that C intersection C is 0. But that's a good contradiction. And the way of doing it is not difficult, just looking at the picture. So, if you look locally, this is not proof, this is sketch of proof. If you look our foliation cycle, well, locally it looks like an integration of currents of integration on disks, or squares in that case, along a transverse measure. So I can write my current or my cycle or whatever, my foliation cycle, C can be written as a sum indexed by the flow boxes of integral along the measure of disks or squares. The square is, this is a simplex, which is the square integration on that square. This square ITI means flow box I, the simplex corresponding to the transverse parameter Ti. So my current is just like a sum of integrals of things like that. Now when you compute the square self-intersection of that object, well, you have a double sum and a double integral and an intersection of simplices like that. And now these disks square ITI are disjoint because this is lamination and this is an embedding. So these things are really disjoint. So they don't intersect at all, except maybe when they are equal. So if you assume that our measures, mu r, have no atom, this means that for almost every choice of pair Ti, Tj, these two chains, square I, Ti, and square J, Tj, are disjoint and intersect. So the intersection of these two cycles is obviously zero. So maybe I said complicated words to say that this is zero because leaves don't intersect. That's it. So this is zero, this is obviously. Now why is it obviously positive? Well, almost the same reason. Well, the idea is just move a little bit the picture and use the very important fact that CP2 is not a complex manifold, which admits a big automorphism group, projective transformations. So what you do is this, you choose a projective transformation from CP2, it's a biholomorphic mapping, and you choose it close enough to the identity, a small perturbation of the identity. And you do the classical trick. If you want to compute the self-intersection of a cycle, if you don't quite know what to do, you move it a little bit to put it in general positions, so to speak. So you want to compute the self-intersection of a cycle with itself. Well, it's equal to the intersection of the cycle with the image of itself by the... You just move the cycle. Now you have two cycles, which are not the same, because the other one is the image of the other one. So let's do the same computation. You have a double sum of a double intersection of square I of Ti with the image of square J of Tj by phi. And the fact now is maybe illustrated by this picture. If you take a foliated chart with one, let's say, like that, by a small motion, the foliated chart, then the two charts will intersect. They didn't intersect before, but after this small motion, these squares will intersect. So square I of Ti and the image of square I of T prime I will intersect for small values of T and T prime. So now, important word is that in complex geometry, when two curves intersect, they intersect positively. This is basic thing. So that this intersection is positive. So that's a contradiction. You have positivity and zero. QED. Okay, so that's it for today. This is but quite disappointing because, you know, this assumption of the existence of a foliation cycle is really not what we want to do. So the program for tomorrow is the following. I want to look at the following question. We know that Riemann surfaces are several kinds of Riemann surfaces according to the universal cover. Universal cover Riemann surface can be either the CP1 projective line, or it could be C, or it could be the disk. So there is this very important distinction to three kinds of Riemann surfaces. I want to look tomorrow at the corresponding statements for Riemann surface laminations. And I want to give some examples that will show that the situation is not so nice, And it could have a very subtle distribution between parabolic, hyperbolic leaves, and so on. So I want to do this tomorrow, and Sunday, as I promised, I will try to embed things into projective spaces. Thank you.
Any questions? Why was this last theorem supposed to be bad news?
Because there was... No, it's not bad news, it's a bad hypothesis. It's good news because it's proving that there is no way of...
He means it might be a small fraction of the real theorem.
Yeah, you're right.
Some fraction of 5% small.
Yeah. So I would like to delete the assumption, existence of a... The assumption is too strong for me.
Other questions?